Hello everyone, in this video I'd like to talk briefly about the Octet Rule. And the Octet Rule you may recall hearing that from your previous chemistry course. So what is the Octet Rule? The Octet Rule says that atoms in covalent bonds are energetically more stable when they have a filled octet, a set of 8 electrons. So let's think back to our electron configuration work, and you may recall how we had electron configurations for noble gases that were 1s2, 2s2, 2p6, right? So the electron configuration for neon has how many valence electrons? Well, it has how many electrons in its outermost n equals 2 level? It has these two in the 2s, and it has 6 more in the 2p subshell. So this noble gas neon has 8 electrons in its valence level. Similarly, for the noble gas argon, we have 1s2, 2s2, 2p6, and then we get to its valence level and we have 3s2, 3p6. So for argon, how many electrons does it have in its valence level? Well, it has 8. 1, 2, 3, 4, 5, 6, 7, 8. If we get down to krypton, noble gas krypton, it is 4s2, 3d10. Notice that 3 is not the valence level because it dropped down a level. So the valence level for krypton is n equals 4, and it has 4s2, 3d10, and then 4p6. So how many electrons does krypton have in its valence level? It has 4s2 of them, and then 4p6 more of them, so 8 electrons. So we're seeing these noble gases that have 8 valence electrons, and they are very stable. And so the Octet Rule reflects that. It says that atoms, when they bond covalently in molecules, they are energetically more stable when they have a filled octet, or set of 8 electrons. And that's why species bond to begin with, is because they're trying to satisfy their need for electrons so they can look like noble gases. So let's take a look up here and see if we can find these octets. How many electrons are around that oxygen in the water? Well, remember that every straight line represents 2 electrons. So this straight line right here represents 2 electrons. That's a covalent bond. So this oxygen has those 2, and 2 more there, that's 4, and 2 there is 6, and 2 there is 8. So this oxygen has a set of 8 electrons around it. Let's take a look at this carbon. It has 2 electrons there, 2 there, 2 there, and 2 there. It has a set of 8 electrons around it. What about the nitrogen in an ammonium cation? 2 plus 2 plus 2 plus 2 electrons around it. It has a set of 8. So the oxygen, the carbon, and the nitrogen are all following what we call the Octet Rule. And that is, they're the most stable when they have a set of 8, a filled set or octet of 8 electrons around them in the structure. Now, even though we say that it's a rule, there are some important exceptions to the Octet Rule. And here's one that you may have noticed already. Hydrogen, right there, this hydrogen only has 2 electrons around it, right? 2 valence electrons around it. So hydrogen does not follow the Octet Rule. In fact, hydrogen only has a maximum of 2 electrons that can be around it. So one of the exceptions to the Octet Rule, hydrogen, which has a max of 2 electrons around it. It cannot have up to 8. And you'll see everywhere else that a hydrogen appears, it only has 2 electrons associated with it. This hydrogen, only 2 electrons, only 2 electrons, only 2 electrons. If we look at the periodic table, a couple of other exceptions are beryllium and boron. Because of their relatively small size, and also because they have few protons to attract electrons, they cannot manage a full set of 8 electrons around them. They are limited to a maximum of 4 and 6. Valence electrons around them. Now, there are exceptions, and I'm not going to get into the exceptions, but for now, for this course, this is going to work for us. So, this is a maximum of 2 valence electrons associated with hydrogen. For beryllium, a max of 4. For boron, a max of 6. So those are exceptions that have fewer than 8 around them. They cannot have as many as 8. There are other exceptions to the octet rule that can exceed, have more than 8 electrons around them. And these exceptions are atoms that have d orbitals. So let's take a look and see which atoms these are. Remember that the d orbitals start with the 3d subshell. This is in the 4, n equals 4 row, but the d subshell takes one number less. So this is the 3d subshell. So which atoms have a 3d subshell available in its valence level, even though they don't have electrons in it? Well, any of the atoms that are up here in the n equals 3 row, phosphorus, sulfur, chlorine, they have access to a 3d subshell in their valence level, because their valence level is n equals 3, right? So in their valence level, they have an empty 3d subshell. They have no electrons in that 3d subshell, but they have access to it because their valence level is n equals 3, and so they can place electrons in that 3d subshell if they need to. So that's what happens. So this is for the third row and lower. If you have an atom that's in the third row, like phosphorus, sulfur, chlorine, or lower, like bromine, and they are a central atom in a molecule. For example, the way this oxygen is a central atom in this molecule, this nitrogen is a central atom in this species. So, when you have atoms with d orbitals, that is the third row and lower, row 3 and lower, they may, and I'm going to circle that, may, they are not required to have more than 8 electrons, but they are allowed to exceed the octet when they are a central atom in the species. And they can exceed 8 up to a max of 12 valence electrons around them. So you could conceivably have an atom with up to 12 electrons around it if it's in the third row or lower and it's acting as a central atom. You may recall an interesting molecule I shared with you a few videos ago when we were doing nomenclature of the xenon tetrafluoride. I'm going to give you an example here. Xenon and the tetrafluoride. Let me give you the formula for it first. Xenon tetrafluoride. And remember I told you that although noble gases don't generally react, in certain very controlled conditions in the labs we can force them to react with fluorine because fluorine is highly reactive. So there's a compound, xenon tetrafluoride, and its Lewis structure looks like this. How many electrons are around that xenon? 2, 4, 6, 8, 10, 12. So there's an example of how atoms that have d orbitals may exceed the octet rule and they may even have up to 12 valence electrons. Okay? So that's the octet rule and some important exceptions.